To start our work with derivatives of logarithmic functions, recall that y equals the natural log of x is true because x is equal to e to the y. Using implicit differentiation, we get, since x is equal to e to the y, differentiating on both sides gives me 1 equals e to the y times dy dx, because on the right we differentiated e to the y with respect to x. Solving for dy dx, we get that that is equal to 1 over e to the y. But x was equal to e to the y to begin with. So dy dx is equal to 1 over x. That is to say, the derivative of the natural log of x with respect to x is equal to 1 over x. If x happens to be negative, then since the argument of the natural log can't be negative, we consider the derivative with respect to x of the natural log of the negative of x, which would give us 1 over negative x times negative 1, that negative 1 coming about because of the chain rule. That gives us actually the same result of 1 over x. Thus, the derivative with respect to x of the natural log of the absolute value of x is equal to 1 over x. This is true provided that x is not equal to 0. It follows that, working backwards, the integral of 1 over x dx is equal to the natural log of the absolute value of x plus c. So we now know how to differentiate the natural log function, and we know that there exists an integral, the antiderivative of which is the natural log of the absolute value of x. That function of which the natural log is the antiderivative is 1 over x, and that actually closes a gap in the power rule. The integral of x to the n dx, when we first saw the power rule in earlier calculus work, we knew it was x to the n plus 1 over n plus 1. That is, we add 1 to the exponent, divide by the new exponent, plus our constant, of course. And that was true as long as n was not equal to negative 1, because if n was equal to negative 1, adding 1 to the exponent gives me 0, which is a problem if I'm going to divide by the new exponent. But now we can say if n is equal to negative 1, we have an answer, and it is the natural log of the absolute value of x plus c. We're going to jump to an example, and it is the integral of the tangent of x dx. It's worth noting that the tangent function is a ratio, right? Tangent of x is equal to the sine of x divided by the cosine of x. And so that becomes our new integral. Now, if we look at what we were just looking at, the integral of 1 over x dx is the natural log of x. So the point here is that the function is in the denominator. Therefore, I'm going to look now at the function in the denominator, and I see that it's the cosine of x, and we're going to let that represent u in a u substitution. If u is equal to the cosine of x, then du is the negative sine of x dx. Therefore, if I multiply and divide by negative 1, then I have an integral that looks like du over u, which could be written as the integral of 1 over u du, which matches what we've been working with here. So the integral of the tangent of x would integrate to the natural log of the absolute value of u. In this case, u is the cosine of x. I forgot the negative out front here, plus a constant. So the integral of the tangent of x dx is the negative natural log of the cosine of x plus c, and that cosine is in the absolute value. But we actually can express this without that leading negative. Recall that if we have an expression r times the log base b of m, that r can act as an exponent on the argument of the log, and we get log base b of m to the r. Here, that coefficient is a -1. Further, the cosine of x to the -1 is 1 over the cosine of x, which we know to be the secant of x. Therefore, if we take the -1 that's a coefficient and apply it as an exponent to the cosine function, then we end up with the natural log of the absolute value of the secant of x plus c. And that's kind of a cleaner look for this differentiation rule because we don't end up with that negative out front. It's kind of nice. Here's another thing. We're going to find out throughout calculus that the secant tends to go with the tangent quite a bit. You've seen it with the derivatives. Think about them. You've seen it with the Pythagorean identity, that the tangent squared plus 1 is equal to the secant squared of theta, for instance. And now we see that the integral of the tangent of x dx is the natural log of the absolute value of the secant of x. Of course, plus our constant.